the exact title otherwise.
There you go.
Okay, privately learning high-dimensional distributions.
Should I start now? We're a bit early. We're ahead of schedule. That's great.
Yeah, we are 4
Wait
minutes.
for the
Yeah, I think we are 4 minutes ahead of schedule. If somebody want to see it live stream, maybe you can start by giving the context of this work.
Sure, yeah. Let me just give a bit of advance warning in some sense. This is perhaps more of a theory talk than you've heard in other talks during this workshop. But that's because I think this is a bit more at, say, the early stages. And I hope that in, say, a couple of years, 1 or 2 years, either myself or someone else in this audience will be able to give a more applied talk based on some of the things here in this talk. And I will say that, like, while it is a theory talk, some of the concerns, which I'll really highlight at the beginning of the talk, are really things that do come up in practical data analysis, which a lot of people this week have mentioned. So, yeah, with that preamble, I'm going to tell you about privately learning high-dimensional distributions. This is a joint work with my friends and collaborators, Jerry Lee, Vikram Singhal, and John Ullman. And I'll mention that some of the slides in this talk were kind of modified from versions of John. As you will see, he's a much better artist than I will be able to, based on some of the pictures. So let's start with the setup of this problem. I'm going to first make a distinction between algorithms versus statistics. And so in algorithms, typically, we have some sort of data set, which is fed into some algorithm, and we get some sort of utility. The quality of the solution is measured in terms of some function of the output y as compared to the input data set x. But today, I'm going to be talking more about statistical tasks, which have seemingly a rather similar setup. But actually, there's going to be a distribution P which generates the data set x. And note that here I've changed the definition of what utility will mean to be in terms of the output y with respect to the distribution P rather than the input data set x. So this is the picture we have here. Then this is the general type of setup. And our goals will be roughly as follows. There's going to be 2 desiderata. The first thing we want is like the statistical accuracy type guarantee. Even ignoring privacy, this is sort of the core thing we would want. We want our algorithm to be accurate. And this is sort of a stochastic guarantee with high probability over the data set generated from the distribution. This may require assumptions about the distribution which generates the data to hold. For example, that it might be Gaussian or have bounded moments of some sort. And today the goal will be to estimate the distribution P. I'll, in a few slides, talk a bit more about what I mean by that. And the second thing, of course, this is a privacy workshop, so we're going to want the algorithm to be private. The one thing I'm going to highlight is that we want our algorithm to always be private. On any sort of realization of this data set X, we're going to want privacy. So let me just sort of emphasize again, this is like we always want privacy, but the accuracy is sort of stochastic, assuming good things happen when we generate our data set. And today I'm going to focus on results mentioning which are in the model of epsilon squared concentrated differential privacy. But don't worry too much about the specific definition. Everything I'm going to talk about today is sort of like for any sort of approximate differential privacy. There's, I think, some very interesting open questions about pure differential privacy in these models, which I'm not going to delve too much into. Yeah. And the general type of question we're going to ask is, what is the additional cost to guarantee 1 and 2 as opposed to just guaranteeing 1? So before I move on, are there any questions about the general setup? Yes.
You might mention that in the next slide, but cost measured as in?
Yeah, in terms of the amount of data you need to get an accurate estimate, or sort of equivalently, what sort of rates you will get as a function of the various number of samples, privacy parameter, et cetera. And possibly other parameters which will come up very soon. We'll see. Good. So I promised I'll start by giving a concrete example of where one of the core problems could come up in data analysis. So imagine we're given a set of female heights, x1 through xn, compute the average height. I'm focusing on female heights just because this should be roughly Gaussian, whereas male and female heights may be a mixture of Gaussians. And also because today is International Women's Day. So this day. So the data set might look something like this. These are heights in centimeters. And so perhaps more mathematically, the question you would want to answer is, given a set of samples xi, which are IID, compute the expectation of the distribution which generated them. OK, so let me ask you, if you wanted to privately estimate the mean, tell me your first answer. How would you do this? Quick, don't think about it too much.
That's it.
Gaussian noise.
Gaussian mechanism, Laplace mechanism. For the purposes of this example, I'm going to say the Laplace mechanism. So we all know that the Laplace mechanism would do something of, I guess we need a normalization factor here, which I neglected. But the idea is we would take the empirical mean and then add Laplace noise. The issue, of course, with just as I've stated this, is what exactly is this delta? What is the sensitivity of the statistic? And if you're naive, then you could have delta equals real max, in the sense that all you know about your data set is that it's going to be somewhere between 0 and infinity. The best you can, sort of what you'll do is you'll have to add noise which is proportional to 1.8 times 10 to the 308, which I'm sure you'll see gives you no sort of accuracy guarantees. So this didn't seem like the best thing, but can we do something anything better than this? Well, one thing you can do instead is use some sort of a priori knowledge you might have about the data, in the sense that suppose I hadn't looked at the data at all, I kind of have a general belief that most females will be between 120 centimeters and 200 centimeters, between, say, 4 feet and 7 feet, roughly. So I can maybe use this sort of information in order to limit the sensitivity of my statistic. In particular, now I want to put these vertical bars here, which are kind of, say, clamping or clipping or Windsorizing, I guess is the statistical term for this, at 120 and 200. And I kind of expect my data to live in here, and this will thus limit the sensitivity of the statistic. However, it's now 80, which is much, much better than 10 times 3 to the 308 or whatever. But the thing is, 80 over epsilon is still a fairly large amount of noise, right? This is something perhaps you'd like to minimize the cost based on this type of uncertainty. Even worse, I claim that things will get worse in sort of high-dimensional settings. For example, this was sort of a univariate problem. If you wanted to do a similar type of clipping in higher dimensions, maybe you'd have an estimate for each dimension independently. But the thing is, this would compose over dimensions. And in fact, you would get something which is, say, dependent on the dimension, a square root d factor, even in terms of how bad your bound is. So this is a challenge which will become especially pronounced in high-dimensional estimation problems. And our overall goal will be to try to minimize the cost due to this uncertainty in our parameter estimates. So this is kind of like our sort of end goal here. We're going to try to get algorithms which have low cost because of this, our uncertainty. Before I continue, are there any questions about this sort of phenomenon? Yes?
By uncertainty, you mean the probability that our bounds aren't justifiable? Like the probability of females with heights that are different, less than 120 or bigger than 200?
Yeah. Well, the idea is we're going to want to have some reasonable belief about where the actual data should lie, in some sense.
And since you're setting this up iteratively, will you adjust your idea about where the data lies based on starting the process?
Yeah, essentially the idea is the way the algorithms will work eventually, skipping ahead a bit, we're going to sort of start with a very coarse estimate, and it'll be possible in some ways to refine the estimate based on statistics of the data. For example, imagine you clipped it at this, and then you estimated the mean based on a lot of noise. Maybe you would see that, actually, perhaps our data actually lives in this interval, and then we can iteratively reduce it. So this is the idea. Ideally, we'd privately add noise proportional to where the data lies, but we don't know that, so we try to privately estimate and iterate.
And how do you measure the difference in mean?
That's a good question. We're going to do it in terms of total variation distance overall, but it can essentially be, if you want to estimate the mean of a distribution, you're going to want it to be something like proportional to sigma over, say, square root n. That's kind of the accuracy guarantee we want, ideally. That's the non-private rate, at least. Cool. So this is just a univariate problem, and in fact, there's been a good amount of work into univariate problems. in the sense, let me just give you an example of the type of theorem you're going to see in this talk. This is just the sort of simplest private algorithm. In fact, this sort of uncertainty problem does not even come up in this problem. And that's, suppose we wanted to estimate the mean of a Bernoulli distribution up to plus or minus alpha, then there exists a private algorithm which does this with 1 over alpha squared plus 1 over alpha epsilon samples. So this will give us something which is biased up to plus minus alpha. And if you prefer rate, this might be a term you're more used to. But I want to compare this with the private cost, which is 1 over alpha squared. So you can see this 1 over alpha epsilon is the kind of additional cost due to privacy. So this is the most basic thing, but also more interesting settings have been studied. I say reasonably well understood. I say this in a theory sense. The first thing I want to mention is a work by Vishesh and Salil from last year, where they have a theoretical result on univariate Gaussians. And I was talking to Vishesh, and I think they've done some work towards making these things actually realizable, going, say, beyond the theory, which I think I'm interested in hearing more about. In terms of other univariate problems we've studied, there's been also work on univariate discrete distributions, say learning them in Kolmogorov distance, and also total variation distance, including some work on structured distributions in total variation distance. But the real question here is, what about high-dimensional data? Can we do anything meaningful for high-dimensional distribution estimation problems? So I'm going to tell you what our results are, and I'm going to present it sort of piece by piece, because it's a kind of a big statement and can be a bit scary, but be brave and I'll walk you through it. So I'm going to show you that there exists a private algorithm which learns a Gaussian. That is, we're going to be given data which is drawn according to some Gaussian distribution. It's going to be d-dimensional, and it has some parameters mu and sigma. This is going to be sort of the quantification in terms of how our uncertainty, in the sense that we're going to be given some upper bound on the norm of the mean, and also some bounds on the how the covariance looks. Just sort of to focus on the first term, the idea is this is similar. How small a ball rather can we draw around the true mean and be sort of guaranteed that our mean will actually be within this ball? So this is kind of trying to capture the phenomenon that I showed you a few slides ago. And this, the second condition is kind of similar except for covariance. This is the natural way to do it, I claim. And if you do this, this is the setup, and this is the oh, sorry, I should mention one last thing. We're going to try to estimate the distribution in terms of total variation distance. This is also known as the statistical distance, L1 distance. If you don't like that, you can also think of it as some sort of parameter estimation problem in the appropriate way, kind of like what Marco was asking, in an appropriate way which is appropriate for Gaussians, yeah. And then if you do this, then the sample complexity will be the following term. Like I said, it can be a bit scary, but let me try to walk you through the terms which are relevant. So if you take a look at the first term, this is actually the non-private sample complexity of this problem. That is d squared over alpha squared. I'll note if you look at the four terms, there's nothing which is really super quadratic in the dimension. We're going to have a second term, which is kind of, if you paid attention to the Bernoulli thing in the last slide, you'll notice that it's kind of the same thing. You know, we have d squared over alpha squared. It's natural to expect a d squared over alpha epsilon. In fact, it's also required. But the main thing, I guess, going back to the story I told you before, we have a mild dependence on these uncertainty parameters r and kappa. In the following sense, recall that we had 80 over epsilon we sort of had an uncertainty of 80 in the example, but we could reduce that to, say, log of 80 in this way. We have some lower bounds showing that some of these dependencies are necessary. For example, like the second term is tight, and we need at least a logarithmic dependence in this type of model. And we also have similar results for product distributions, which I'm not going to talk about today. Okay, so before I continue, is there any questions about the statement itself, the theorem, or how it maps to what we discussed before?
So your premise that there is a bound kappa on that. If you don't know kappa, since you're like private no matter what, can you do some kind of doubling search and like test whether like what you've learned is good, and like so that algorithm would actually not know kappa beforehand but figure it out on the fly?
A kappa-free algorithm in some sense. That's a good question. Like I said, you sort of have to pay. There is a lower bound based on that term. You can't really deal with the case where it's
I mean,
Let me revise that. I'd have to think about it a bit more, but my immediate impression is no, but I see what you're saying. Yeah. Any other questions? Salil?
Yeah, if I recall correctly, yeah, at least for pure DP, you need a dependence
Yes.
on kappa and R, and that probably is true also for concentrated.
but you wouldn't have paid it.
Just maybe to quickly respond, like, at the end, the sample complexity may have a dependence on kappa, but you maybe don't need to know kappa ahead of time. You just, at the point when you like are done, you will have used like log of kappa many samples, but you don't need to like start knowing what it is. Does that make sense?
Yeah, I wonder. I mean, I wonder from in the privacy definition whether
Whether it makes sense.
yeah, but that's interesting.
It's a good subtlety, which I think I'd have to think about when I'm not at the podium, because my IQ's dropped 30 points in front of an audience.
So
Yeah.
this is in terms of total variation. So I guess if you want to think of it in terms of the distance in parameters, this I guess will mean that you must be close to like the right mean in some way that depends on the covariance.
Correct, yeah. It's sort of in like the Mahalanobis distance, which is sort of like rescaled by the covariance. I'll show you exactly what I mean, at least for the covariance case, which I'm going to focus on today, because I think that's more technically interesting. But yeah. One sort of thing related also to the sort of discussion about whether or not this is required. Let me note in the pure and concentrated cases, we know that we have a log dependence. For the high dimensional problem, it's currently a good question whether you can get completely kappa free. In a one-dimensional case, in Vishesh and Salil's paper, they do get rid of it. So yeah, this is an interesting open question that we're looking at a bit more in high dimensions. But either way, this is getting a bit into the details for probably much of the audience. So I'm going to continue. Any other questions? Yeah.
One quick question. So in this product distributions case, you go from D squared to D. So is there a way to get a result that kind of like smoothly interpolates between these two settings?
So let me mention this is binary product distributions, is not for Gaussians.
Okay.
That said, there is a good question, or there's also the question if you just want to do mean estimation of a Gaussian. If you know the covariance, it's kind of like also D. If you don't know the covariance, then actually the best algorithm we know of is D to the 3 halves. This is a kind of an interesting phenomenon. I'll be happy to talk about it more offline, though. Cool. And in today's talk, I'm actually going to focus on a simpler version of this problem. That is the case where the mean is 0, and talk about how to do covariance estimation. Because I think this is kind of where some of the neat techniques come in the high dimensional case. Let me note that if kappa were small, that is sort of we had a very good estimate already of what the covariance is, then this problem would be very easy. As I'll show you in a few slides, I'll tell you a very simple algorithm for it. But the challenge is sort of when our uncertainty is very large, and we give a private recursive method to reduce the condition number. Okay, so the question is, what is learning a multivariate Gaussian? There's the question of learning in TV versus learning in parameter distance. I'm going to flash some sort of scary-looking equations on that side of the board, and then I'll show you a nice picture, which is usually how I like to think about it. So we're going to be given samples from some Gaussian like this, and we want to output a covariance, sort of a proxy for the covariance, with the following property. We want it to be close to the true covariance in this funny norm up to alpha. And this funny norm is sort of equivalent, that's kind of the rescaled version of the Frobenius norm. You can stare at this if you want, if that makes sense, great. And this will give you low total variation distance. But perhaps the more intuitive way of thinking about it is often we picture covariance matrices as a sort of ellipsoid. So you can see this red one is the true ellipsoid, the true covariance. But we're going to have something which is approximately it. And you'll note that this is sort of like a relative, it's a multiplicative approximation in kind of all directions. In the sense you see this thin direction, it's going to be a fairly close approximation, but we have a bit more leeway in the long directions. So up to sort of like a multiplicative factor in all directions is what we want. Okay, so let's start by talking about how we would non-privately learn a Gaussian in this setting. So we're given a data set x1 through xn from this distribution. And I think we all know, or it's known that you can output the empirical covariance, and this will be a good estimate. In particular, the accuracy you're going to get is something like this. So in particular, if you set to n to be d squared over alpha squared, you can get the total variation guarantee that I mentioned before. And the question is how to privatize. Well, of course, like we sort of discussed before, maybe the Gaussian mechanism would be a nice thing to try. I'm going to give you a quick recap of the Gaussian mechanism. I guess this should be pretty familiar for most of you. So let me just state it first for the univariate setting. We're going to look at the sensitivity of the statistic. Yeah, this should probably be familiar to many of you, so I'll go over it a bit faster. But the idea is we're going to take the non-private statistic. We're going to add Gaussian noise proportional with a standard deviation proportional to the sensitivity over epsilon, and then output that. And it can be shown that this is epsilon. This is appropriately private. And the one thing maybe which you have to think about for a sec is how accurate is this? Well, I claim just due to like Gaussian tail bounds, this is sort of going to be within a constant number of standard deviations. So the accuracy will be something like this. It will in fact be like about sensitivity over epsilon. Okay, but we're dealing with high dimensional problems. So in fact, we're going to raise everything to we'll look at d by d covariance matrices. And in particular, this is just going to be the following. It's going to be the same sort of natural generalization. The idea is you're going to add independent Gaussian noise to each entry of the covariance matrix. And that's the Gaussian mechanism. It'll be appropriately private and give you this type of error guarantee, accuracy guarantee. If you're familiar with the paper Analyze Gauss by Dwork et al., this is kind of like the main algorithm they have in their thing. And they analyze Gauss. But OK, so this is the first method that we're going to look at. Let's try private covariance estimation. So again, we have some data set. We're going to output now the empirical covariance matrix, but with Gaussian noise added to each entry. The accuracy guarantee we're going to get is the following. The issue is, what is the sensitivity of the statistic? If you remember the example at the beginning, we're going to run into very similar issues. In the following sense, we imagine that our data set should look something nice like this. It's a nice Gaussian, sort of near zero. But the issue is that this isn't actually, in this setting, the empirical covariance is rather sensitive. For example, you could have one point which is placed out here, and this would cause the empirical covariance to shift from something maybe more like that to something like this. I'm being a bit, yes?
The covariance matrix is symmetrical.
Yes, it will be a symmetric matrix.
You're adding noise to each of the, you're not sort of accounting for the fact that the upper diagonal has to be equal to the lower diagonal?
That's fair. Like if you want to, the actual algorithm will be adding it, say, to the upper the triangular part, upper triangular part, and then mirroring it with the exact same noise. So yeah, you can see that this is a rather sensitive statistic a priori, because one data point could go anywhere, and this could arbitrarily shift the covariance matrix empirically. So in other words, we've got an n equals O of infinity sample algorithm, which is not great. I guess we can deal with machine precision if you want, but no, we'll skip that. But the idea is we can use a very similar idea first in order to do something similar to what we did in the height example I gave at the beginning. The idea is we're going to limit the sensitivity of this via truncation. Now what we know is we have two bounds. We know that the covariance is greater than the identity. So nothing lies within this inner circle. And also the covariance is upper bounded by kappa times the identity. So nothing lies outside the outer circle. And therefore, sort of the worst case for how much we can shift the covariance is bounded by how much this guy will pull our covariance matrix. So this is the main idea. And we're going to sort of edit our algorithm before to sort of take into account. Like I mentioned, this is kind of going to be a rescaled version of Analyze Gauss. And I'm going to call it the truncate then empirical method for a reason that'll be clear later. Or I guess when I tell you, it'll be pretty evident why this is truncate then empirical. We're going to first truncate by removing every point which is too large. That is, take me at faith when I say that if the data actually came from a Gaussian, which has these properties, then this step will essentially do nothing. This is not useful for the stochastic guarantee, but this will be useful for the worst case data privacy, because now we are limiting the sensitivity. And this will in fact bound delta to be O tilde of kappa times the dimension. So now we're going to, given this sort of Windsorized data set, or either Windsorized, truncated, whatever you like, then we will have this statistic where you compute the empirical covariance, and then you add Gaussian noise of the appropriate magnitude to each entry of the covariance. As I sort of mentioned before, this will give you accuracy, which has this sort of guarantee here. And if you sort of invert this to see what sort of total variation guarantee this gives you, this tells you that if you want to estimate up to alpha total variation, you have the following sample complexity. So let's distill this and see what we have so far. I'm claiming there exists a private algorithm which learns the Gaussian in total variation distance with this sample complexity. You'll note that this is actually pretty close to what we want, except for this pesky factor of kappa right here. If kappa was O of 1, then we would be done and we could call it a day. The issue is sort of due to this type of uncertainty that I mentioned. Kappa could be very large. So any questions about this statement before I continue? Why this is a good baseline, but not great when we have a lot of uncertainty? Yeah.
Quick question. So when you're looking at the difference, I've sort of figured out the formula. You're inverting sigma hat or the original sigma?
So this is sort of like a worst case for anything in that. So kind of I think the worst case would be if it actually is the identity. And so yeah, this is like...
But this is sort of why you need it bounded away from I, because if you invert it and you're close to singular, it'll destroy everything.
Exactly, then it would give you no total variation guarantee. Yes. Cool. So let's try to see what exactly went wrong with this algorithm. What really, where did we lose here? And the idea is as follows. Suppose we had a lot of samples that is bigger than kappa times the dimension squared, then our noise would be small. In a sense, the red ellipsoid is the empirical covariance, the true covariance, and then our noise will be somehow small. If we add it on, you can see we get the sort of guarantee that I mentioned, in the sense it's close in every direction up to this amount we want. In other words, if we have a lot of data, our noised empirical covariance will be close to the true covariance. The issue is if this condition here does not hold, in the sense that if n is smaller than kappa times dimension squared, then it'll look something a bit more like this, where if you add it, you get this sort of rather more spherical looking covariance here. In other words, if you take a careful look at this, you'll note that we have a noised empirical covariance, which is pretty good estimation in the long directions, but somehow in the short directions we don't have as good an estimate. So our goal for algorithmically will be to try to discover and add less noise in these short directions in order to like refine our estimate and get something better. Okay. And yeah, like I said, the noise outweighed our signal in the small directions. So our goal will be to approximately learn sigma in all directions. And the key like algorithmic primitive which we'll have to do this, sort of how we would formalize this, is by saying there exists a private algorithm which finds a matrix A hat, which we'll call a preconditioner. And the idea is if you sort of rescale the covariance by this preconditioner, that'll put it in approximately isotropic form, up to a factor of, say, 100 or some constant factor. And the sample complexity of this will be d to the 3/2 logged square root log of kappa over epsilon. And you'll notice this was one of the terms in our sample complexity before. And suppose we had this algorithm. I'm just going to state this. In fact, I'm not going to get into the details in this talk. But suppose we had this algorithm. This is how we would use it. The idea is we start sort of in the regular domain. This is the problem. Now we're going to first learn a preconditioner, which will try to make it more spherical and try to say that's between the identity and a constant times the identity. What we're going to do then is learn the distribution, learn the covariance in the sort of transformed space. And then by an appropriate rescaling, we shift back to the original space. So this is the image, and pretty much the next slide, which will be about my last technical slide, will sort of formalize this. We're given some data set. We're going to first learn this preconditioner that I mentioned in order to put it in roughly isotropic form. we're going to do the truncate and empirical method, the thing I presented in a few slides ago, on the data set, but now we're going to precondition it by multiplying by this sort of transformation matrix. And then we're going to output the covariance, which is sort of rescaling back to the original domain. This is sort of what I showed you in a few pictures in the previous slide. So step 1, the first step to learn this preconditioner is going to be this sample complexity. And the second step, now you'll notice that, remember I told you this is the sample complexity, kappa times d squared over alpha epsilon. But because now we have this condition, we have it sort of appropriately conditioned, then this will just be the right sample complexity. So we can check that off. The one thing you might be wondering is how exactly do we do step 1? I'm not going to talk about that in this talk. So let me hurriedly click through slides where I was going to talk about this. But OK, basically, just to sort of conclude, we have this algorithm which learns the Gaussian with these sort of this sample complexity. We give the first algorithm for privately learning Gaussians and product distributions in high dimensions. And it's the first one with mild dependence on these uncertainty parameters, and showing that privacy comes at sort of a small cost in these settings. Thank you.
Questions?
So the preconditioning is sort of like principal component, something like this. You're basically trying to downscale those later dimensions.
Yeah. The idea is to try to find which direction they're long, which direction they're short. The question is how to sort of do this without taking d squared samples and paying a lot. Yeah.
How much does the preconditioning rely on the fact that it's a Gaussian compared to just like an arbitrary distribution with good concentration?
Yeah, I think this is it's likely possible that we could sort of relax the assumptions a bit in the sense that we just have, since it's a Gaussian, we'll have certain types of concentration. It's likely possible that you can, as long as any distribution which satisfies that type of requirement, you could also run it on. This is something which I think some of us are thinking a little bit more about, but hasn't been sort of at the top priority. Cynthia?
You remove the long points?
Points which are very far away, yes.
Rather than just shortening them.
Winsorizing, I guess, yeah, is the term I used.
Can you explain that choice or say something about?
Sure. So the thing is actually if the data actually came from a Gaussian, this would actually make no difference at all in the sense that I truncated or removed points which are they wouldn't actually be sampled ever except with like very, very small probability. Mm-hmm. So in terms of the statistical accuracy, that should not make a difference except in terms of the noise you add. Perhaps if you want to make this more practical, it might actually be reasonable to be more judicious in terms of how you truncate and clip things. And then you would be able to add less noise at the cost of maybe losing some of your data. But yeah, in terms of whether to truncate versus clip or Winsorize, they're all roughly equivalent in my mind from a theoretical standpoint.
Okay, let's.
Do you have time? I don't want to go
Sure.
over. Well, I'm just sort of curious about the lower bound of I. Because for most data analysis, in these sort of high-dimensional contexts, usually you feel like there's some major directions which are important, and then you get these sort of noisier directions. So it seems this sort of lower bound of identity seems unnatural to me, but maybe there's rescaling which makes it clearer or something.
Yeah, it's fair. I think there's some things you can do, like you think some directions might be degenerate, say, or?
That's the typical sort of view, right? I mean, that's sort of the motivation of principal components, right?
Yeah, that's fair.
Learning sort of the key structure and everything else is sort of not very important.
Yeah, I know in, say, approximate DP, it's possible to even like get rid of the low, I believe it's possible to get rid of the dimensions which are degenerate in that sense.
But is it because of the metric you're using, just total variation? I mean, this is just too sensitive to having these.
It's plausible. I would have to think about it a bit more, but yeah, it's kind of like, because if you get anything wrong in sort of a flat direction, that's automatically total variation, distance 1.
Right.
So it's plausibly because of that. The question is perhaps what's a better way to estimate? What's a better metric?
Correct over distance.
Plausibly, yeah, maybe it makes sense. Salil?
But maybe since the dependence on this kind of ratio between the upper bound and lower bound of the covariance is only logarithmic, at least in theory, you could use like as your lower bound not I, but some like really tiny multiple of I, and really only if it's like 0 in some directions would you run into trouble.
Okay, but usually those small eigenvalues are running to 0 quite quickly as the dimension grows, right? I mean, polynomial at
Right, but log is like the number of bits of precision there, which in theory is okay, in practice probably is not.
All right, I suggest that we delay further discussion to the lunch break, and let's thank Gautam